dissipative systems. But first, let's review some ideas from before about Hamiltonian systems. Recall that we had the following motivating example. Let's consider the two-dimensional autonomous system dx dt equals y and dy dt equals negative x. We can find the general solution as x of t equals a constant a times cosine of t minus a phase angle phi, and y of t equals negative a times sine of t minus a phase angle phi. In particular, the solution, capital Y of t, satisfies the expression x squared plus y squared equals our constant a squared. More generally, say that we have a two-dimensional autonomous system, dx dt equals f of xy, and dy dt equals g of xy. Can we find a function, capital H of xy, such that all solutions, capital Y of t, satisfy h of xy equals c for some constant c? We found that in some cases the answer here is yes. First, observe that there exists a function capital H such that f is the partial of h with respect to y, and g is negative the partial of h with respect to x, if and only if the partial of f with respect to x equals negative the partial of g with respect to y. If this is the case, then all solutions, capital Y of t, satisfy h of xy equals c for some constant c. Moreover, in this case, equilibrium points are either saddles, nodes, or centers. They are never sinks, sources, spiral sinks, or spiral sources. Such a system is called a Hamiltonian system, and we call h of xy the energy function. Curves of the form h of xy equals c are called level curves. They are plots of the solutions as we let our time vary. We also discussed why h is called the energy function. Say that we have a mass m attached to a spring and let L of t denote the length of the spring at time t. We will assume that there are three forces acting on this mass: gravity, a restoring force due to the spring, and a damping force that will be proportional to the velocity. We refer to this situation as the unforced harmonic oscillator. If we denote x of t as the displacement from equilibrium at time t, then we find the following two-dimensional autonomous system. That is, dy dt equals a times y, where y is the vector x comma y, and capital A is the matrix 0, 1, negative q, negative p. We can show that this is a Hamiltonian system if and only if it is undamped, that is, p is equal to 0. The level curves in this case will be circles and ellipses. Our 1/2 kx squared is the potential energy, while 1/2 my squared is the kinetic energy, such that the scalar m times our function h is the total energy of the system. We'll use this so that today we can discuss dissipative systems. Let's return back to the unforced harmonic oscillator as we just described. We discussed what happens if the system is undamped, that is p is equal to 0, but how do we study the system if it is damped? That is, more generally, p does not equal to 0. For any p, let's say that capital Y of t, namely x of t comma y of t, is a solution to this system. Recall that the total energy is the sum of the potential energy and the kinetic energy. Let's write this E of t as m times h, that is 1/2 kx squared plus 1/2 my squared. If we take the derivative of the energy with respect to time, we realize that this is m times the partial of h with respect to x times dx dt, plus the partial of h with respect to y times dy dt. Substituting in, we find that this derivative is equal to negative b times y squared, which is always a non-positive quantity. That is, it's less than or equal to 0. We can conclude that since this change in the energy is negative, the energy is being dissipated precisely when b is positive. In other words, energy is being lost when there is friction. We'd like to see if this follows a more general phenomenon. Let's consider a two-dimensional autonomous system of the form dx dt is f of xy and dy dt equals g of xy. First, there exists a function g of xy such that f is the partial of capital G with respect to x, and lowercase g is the partial of capital G with respect to y, if and only if the partial of f with respect to y equals the partial of lowercase g with respect to x. In this case, all solutions, capital Y of t, satisfy the following. dc dt is less than or equal to 0, where c of t equals negative g times negative g evaluated at x of t and y of t. Moreover, in this case, equilibrium points are either saddles, nodes, sinks, or sources. They are never spiral sinks, centers, or spiral sources. Any system satisfying these equivalent criteria is called a gradient system. Any function L of t says that if we write c of t is L of x of t comma y of t, and it satisfies c prime of t is less than 0 for any solution capital Y of t, is called a Lyapunov function. Intuitively, we want to think of L of xy as a measure of the energy, so that c of t is the energy at time t. Systems which have a Lyapunov function are sometimes called dissipative systems. Let's explain why this result is true. We'll discuss the first statement. Let's assume that f and lowercase g are partial derivatives with respect to some function capital G. Then it's rather easy to see that the partial of f with respect to y equals the partial of lowercase g with respect to x. Conversely, let's assume that the partial of lowercase f with respect to y does indeed equal the partial of lowercase g with respect to y. We're going to choose a function capital G as the sum of two functions j and k, where j and k are the integrals you see here on your screen. Capital J will be the integral of lowercase f with respect to x, and capital K will be the integral of negative partial of j with respect to y plus lowercase g, all with respect to y. First, observe that capital K is only a function of y alone. That is, if we compute the partial of capital K with respect to x, then we find an integral involving negative partial of f with respect to y plus the partial of lowercase g with respect to x, and we know that this difference here is 0, so the partial of capital K with respect to x must be 0. Hence, capital K is a function of y alone. Second, we can compute the partial of capital G with respect to x. We find that this is just equal to the partial of j with respect to x. And now, from the fundamental theorem of calculus, since capital J is the integral of f with respect to x, the partial of capital J with respect to x is just equal to f again. And finally, we can compute the partial of capital G with respect to y. This is equal to the partial of capital J with respect to y plus the partial of capital K with respect to y. As we mentioned earlier, if we simply realize that we have integrals here, then we can just cancel various items out, and we find that we just have this expression involving lowercase g. Let's show the second statement. First, say that capital Y is the solution, and let's denote c of t as negative g, where we evaluate x of t and y of t. Now we'll take the derivative of capital C with respect to time t. We realize, using the chain rule, that this is the partial of c with respect to x times dx dt, plus the partial of c with respect to y times dy dt. Making substitutions, we find that this is equal to negative the following quantity: the square of the partial of capital G with respect to x, plus the square of the partial of capital G with respect to y. Since the sum of squares is greater than or equal to 0, its negative is now less than or equal to 0. Let's show the third statement. Let's say that y sub 0 is an equilibrium point for our two-dimensional autonomous system. We can perform a linearization around this equilibrium point to find a 2 by 2 matrix capital A in terms of numbers lowercase a, b, c, and d. We can express all of these in terms of partial derivatives of our function capital G. Observe that lowercase b equals lowercase c, so that we have trace indeterminate capital T, which is a plus d, and capital D, which is ad minus bc. Now we can compute capital D minus capital T squared over 4 to find that this must be less than or equal to 0. In particular, D is less than or equal to T squared over 4, so that the eigenvalues of our matrix capital A must be real numbers. This means that the equilibrium point y sub 0 cannot be a spiral sink, a center, or a spiral source. Let's give one final remark here. What we've shown now is that any gradient system has a Lyapunov function and hence is a dissipative system. However, there are dissipative systems which are not gradient systems. For example, we can consider the two-dimensional autonomous system dx dt equals negative x plus y and dy dt equals negative x minus y. One checks that this here is not a gradient system. However, it is a dissipative system because it has a Lyapunov function L of xy equals x squared plus y squared. Let's end today with the final motivating question. Can a two-dimensional autonomous system be both a Hamiltonian system and a gradient system? Well, such an autonomous system must satisfy the following two equations. The partial of f with respect to x equals negative partial of g with respect to y. This is what it means to be Hamiltonian. And the partial of f with respect to y equals the partial of g with respect to x. This is what it means to be a gradient system. Substituting one into the other, we now find that the second partial of f with respect to x plus the second partial of f with respect to y must be 0. This equation is typically called Laplace's equation, and it is an example of a partial differential equation. In this class, we're only concerned with what are called ordinary differential equations, but there are other mathematics courses which do discuss partial differential equations. We give an example to explain how one might actually solve such an equation. In this case, one knows that f must be a harmonic function. That is, there exists a differentiable function, capital F, which we can write in terms of lowercase g plus I times lowercase f, all expressed in terms of a complex variable z, which is x plus iy. Simply put, if we have a function capital F, which is a function of a complex variable, we can write lowercase f as its imaginary part and lowercase g as its real part. These functions would now be solutions to Laplace's equation. Thanks for watching.